Our objective in this miniature world is to transport a package of concentrated nutrients across a wooden desk to reach the soil below. To get there, our liquid agent must navigate the unique physics of a micro-scale environment. When liquid water strikes the floor from a height, the impact forces it into a flat, wide disk. Within milliseconds, the internal pull of the molecules retracts the fluid into its original spherical shape. On a surface with no friction, like a microscopic plastic raincoat, the water has no grip. Gravity dictates its movement, pulling the droplet down the nearest slope. In this baseline state, the water and nutrient cargo are restricted by gravity and surface texture. To move upward or change direction, the fluid must find and use microscopic structural pathways. That pathway appears as a wall of microfibers. Upon contact, the droplet divides into separate water lines that begin to thread through the fiber gaps. Water molecules adhere to the narrow walls of these tubes. The attraction is strong enough to pull liquid upward against gravity. This is capillary action. It allows plants to move water to their leaves and gives our agent a highway through narrow vertical spaces. Liquid water is not a passive substance. Its internal cohesion allows it to use narrow environments to move against the pull of the earth. When the water pulls together, the molecules at the surface create an elastic barrier. This surface tension allows the liquid to overfill a space without spilling over the edge. This molecular attraction acts like a trampoline. When a dense object, like a metal pin, is placed on the surface, the water surface curves to support the weight, keeping the pin and the nutrient package afloat. On a lotus leaf, nanopillars force the water into a sphere. As the droplet rolls, it collects dust particles and debris from the surface, effectively cleaning the leaf as it carries its cargo forward. When the water enters a new container, such as a star-shaped glass, it loses its spherical form and fills every corner, taking the exact geometry of the vessel. The liquid state provides the ultimate versatility, acting as a support structure, a cleaning tool, or a shapeshifter for its surroundings. When thermal energy is removed, water molecules lose speed. Instead of sliding, they lock into a fixed hexagonal pattern. As ice forms, the molecules push outward to maintain this structure. This expansion increases volume, creating enough pressure to shatter the glass container. Now a solid, the water possesses a fixed shape and mass. This ice block moves with enough force to violently smash through plastic bricks. By losing heat, the water trades its fluidity for a fixed shape, gaining the structural power to clear obstacles. If heat is reintroduced, the solid lattice breaks down and the ice melts back into a liquid state. If the temperature reaches the boiling point, the water reacts to the heat. Droplets on a hot surface bounce and sizzle as they begin to change phase. This diagram shows the effect of extreme heat. The molecules move with so much energy that the bonds holding them together break, allowing individual particles to move independently as a gas. Massive thermal energy releases the water from both shape and volume constraints. It is now a vapor, capable of moving through the air. In this gaseous state, the water is light enough to ride air currents. This allows the vapor to travel over the desk and obstacles the liquid could not climb. This flight ends when the vapor meets a cold surface. The drop in temperature causes a sudden change in the physical behavior of the molecules. As the vapor hits the cold glass, it reforms into liquid droplets. The heat keeping the molecules apart is gone, and they pull back together. This is condensation. By losing thermal energy, the gas molecules slow down and re-establish their liquid bonds, returning to their original fluid state. These phase changes are driven by environmental temperature, making the state of the water a direct reflection of the energy in the room. Now back in liquid form, the water falls from the glass and sinks into the soil. Here, the nutrient package is finally deposited, reaching the roots where it is needed. Once the sun warms the surface again, the water evaporates, leaving the nutrients behind and starting a new journey back into the atmosphere. In this single environment, we see all three states at once. The solid ice provides structure, the liquid provides transport, and the gas provides movement. By moving between these states, water creates a cycle that sustains the natural world. It is a continuous physical process that ensures the delivery of essential elements across the globe.